So we're going to pick up where we left off in class yesterday, and then we'll do some review. I was talking to Aaron here just before class, and I recommended a few problems to review to help you understand this better. Problem 323 would be a good one to help you, I think, put a lot of pieces into place. And this is where the entire Appendix A, review of material you've never learned, is beneficial. So I'm going to try to go over the important things you need to know for linear algebra in class today, just to make sure you have what's important. And I do feel a little guilty about not having any homework on this material and then having a test that's going to cover it. That's why I'm naming a few problems to do here. And remember, you can always find the solutions online. I've got the link in the Moodle page. But I was doing some grading of your previous homework, and you've had some hard homework. You deserve a break.
Yeah.
I appreciate it. So let's get started. So this here is the problem we ended with last class period. So I'm going to actually, you know what, change my mind on the fly. Let's actually look at the problem I just recommended, 3.23. I don't know why I prepare for class when I change my mind right as soon as I start lecturing. So problem 3.23, it gives us a Hamiltonian. And since I actually spoke about this very briefly with Aaron, I'm going to direct my question that I'm going to ask here in a second specifically to Chad. I actually have to look up to see who's the other student. How good is my memory? What? Okay, we're given this Hamiltonian, and it says that 1 and 2 are orthonormal basis. E is a number, a real number, with dimensions of energy. Find the eigenvalues, the normalized eigenvectors, and then was the matrix H representing this Hamiltonian with respect to this basis. So right off the bat, how do I make a matrix for this Hamiltonian?
Well, you can do rows and columns.
Yes, but I want to remember the equation that we had from the last lecture. I believe it can be summarized like that. I'm sure I can find it real quickly. It used E sub n's and not just n with what we had, but it was something to that effect. It was like the first thing. You can see where my understanding is. I know how to do it, and I don't remember all of our nomenclature. I had it like as the first picture in the presentation, or first equation in the presentation yesterday. And I truly don't see it, but, oh, there it is. Equation 381 says E sub n, Q operator, E sub n is defined as QMN. So this is equation 3. So Q sub Mn are the values in the matrix if we write the Hamiltonian as a matrix. And so all I have to do is say Q11 is equal to 1 H1, right? And likewise, I just don't like that color. Q12 is equal to 1 H2. Q21 is equal to 2 1, and Q22. And I'll admit to a weakness. I never remember if it's row column or column row for those little suffixes, which is really bad to not remember. But if I do this math, that's going to be 1, and then this whole thing. Now notice, if I close this with a 1, I will get 1. If I close it with a 2, I'll get 0. And so that means that only the two that have a 1 will give me non-zero. And then this one has a bra 1, so it needs to be closed with a ket 1. This one has a bra 2, it needs to be closed with a ket 2 if I'm going to get something other than 0. So I can look at this and say, okay, opening with a 1 and then closing with a 1 means I have to have 1, 1. This is the only term that's going to contribute to there. Right, if I put the 2, 2, I'd have bra 1, ket 2, that's 0. And then I'd have E, bra 2, ket 1, that's also 0. 0 times 0 is still 0. And if I, for instance, used this one, I would have had bra 1, ket 1, that's 1. And then I would have had bra 2, because the 2, the circle there, ket 1, that's 0. So I still would have had 0. Are you not following?
I'm not following.
Okay. Then I was hoping to not write this long thing out. I will write the long thing out. I'm going to zoom in so I can write it a little smaller. What was that, Chad?
Chad's just been a smart aleck today.
Was he saying we have to do this all the time in our homework? Okay, so there I put my operator inside. And now that's going to give me 4 terms. All of them have E, so I'm going to factor out the E. And the first term is going to be 1, 1, 1, 1. So that's kind of funny, actually. Okay. That's that. So actually, I should have kept my color coordination right. So the black is what was black up above, and the red is the blue that I have the funny green lines for. Minus bra 1. I don't know how I miss when I go to ket 2, bra 2, ket 1. So there's my second term. Plus bra 1. Ket 1, bra 2, ket 1, and finally plus bra 1, ket 2, bra 1, ket 1. With the parenthesis at the end here, yes, have room for it. So there I have, except for the first one where I used red, the color coding is the same. And I guess I should have made that blue as well. But now when we look at these, because of orthonormal relations, this is 1, this is 1, this is 0, that's 0. This is 1, that's 0, that's 0, that's 1. So 0 times 0 gives me 0. 1 times 0 gives me 0. 0 times 1 gives me 0. But 1 times 1 gives me 1. And so the end result of all of this is that Q11 is equal to E. So we found the first spot in our 2 by 2 matrix. So now, Aaron, do you understand what I was trying to do when I was trying to take shortcuts?
Yeah, sorry for making you write it down.
No, it's fine. It's really important that you understand it. not the time we spend in class is not as important as the understanding you leave class with. So now for the next one, zoom out so I can see the next one. The next one is 1, 2. So I look at these and I say, okay, which one is going to give me 1 times 1? And so if I have a bra 1 at the beginning and a ket 2 at the end, I have to have one that has a ket 1 and a bra 2, which is this term. And so since that has a plus sign, it had E out front, that's also equal to E. So now I'm going to go to Aaron and then finally Chad. So Aaron, what is Q21 going to be? Which term is it going to match with?
The last one.
Okay. And so that's a plus. So what do I get?
E.
And Chad, which term is 2, 2 going to match with?
The negative or minus 2, 2.
Okay. So what do I have for that value? So now I can make my matrix.
So with bra ket notation, if you have 1 and 2, why is that automatically 0?
It wasn't automatically 0. When I had 1 and 2 here, this one here was the one that did not give us 0.
Right, but when you have like in the
Oh, I understand. I understand what you're saying. You're saying why is this automatically 0? Because it tells us that it's an orthonormal set. So that means that 1, 1, because it's normalized, that's 1. 1, 2, because it's orthogonal, is 0.
So basis means the same thing as set?
The basis means the set of vectors.
Okay.
And there's, as we'll see as we go on today, I mean, are we going to have time for review with all the problems I'm doing? I don't know, but we'll learn things.
Review, right?
Well, it's preparing for the test, but it's new material, which, like I said, your understanding is really important. Okay, so what we've been able to do is, first of all, we've converted this Hamiltonian written in bra ket notation into a matrix. And now with this matrix, we want to find its eigenvalues. So now we have to go through the process of finding the eigenvalues for a matrix. So it was all new to you last class period. There's our Hamiltonian operator. So step number 1, and I actually have the step here. To solve for the eigenvalues of the operator A, set the determinant of A minus, and this here is supposed to be the unit vector, times lambda, equal to 0. So if that's my operator, then my characteristic equation is the determinant of E minus lambda, oops, I forgot my sign there. So that's the characteristic equation. That is what I'm solving to find the lambdas. I will find here 2 lambdas, and that will be my 2 eigenvalues.
What made you put the E's in that order? Did you have to 1, 1, 1, 2?
I put the E's in that order because that's what we found right here.
Yeah.
Whoops.
Like, you would know to put like 1, 2. Like what if 1, 2 had been negative E?
I might have made a mistake because like I said, I get row and column confused. We can look. I'm sure somewhere it's going to say what the standard is in the nomenclature. And, I should know this. And it's not like I haven't learned it 70 times. But I'm not going to spend the time trying to look it up. It's something. I mean, you can just Google real quick. Which do you list, the row or the column?
Should
a
we know
matrix.
how to do that for the test?
Know which subscript is row, which one's column. No, I'll tell you if necessary. Okay, so now, how do we do the determinant for this? This is the easy case. Okay, we do the cross. So we're going to have E minus lambda times minus E minus lambda, and then minus the other direction. And let me color code this. I know you guys probably both know this, but it's always best to be clear. So minus for the second one equals 0. And now in this case, it's not as easy as what I had yesterday because I'm actually going to have to multiply through. Minus E squared minus E lambda plus E lambda plus lambda squared minus E squared equals 0. There I've multiplied through. The first 4 terms are the blue, the last one is the red. These two add together to give me minus 2E squared. These two subtract out. So I have lambda squared minus 2E squared equals 0. So what's lambda equal to?
So minus E root 2.
And that plus or minus, in quantum class, you realize those math rules that we always ignore are really important. If you forgot the plus or minus, you only have one root instead of 2. And we need to have both of them. So, what have we found?
The eigenvalues.
We have found the eigenvalues. What are the eigenvalues for this problem? Remember, we started with a Hamiltonian. I came here just so we could get to the statement problem.
The energy?
Yes, they are the energy eigenvalues. So basically, we could say energy 1 is equal to E root 2, and energy 2 equals minus E root 2. Now, the question is, what are the eigenstates that go along with this?
Use the other formula to plug in the eigenvalues.
Actually, it's not the other. It's the same formula.
Yeah, the form.
Yeah. So I'm going to take my Hamiltonian matrix, multiply it by some unknown state 1. Well, equals E1 state 1. Or in other words, E minus E times AB equals E root 2 times AB. How many equations do I actually need to multiply through from this? Well, let's start with another question. How many equations do I technically have written here? 2. How many do I need? 1 less than that. And it's always 1 less than that. So if it had been 3, then I would have needed 2. So I'm just going to make 1 less than that. So the top one, EA plus EB, that's first times first plus second times second, doing the rows in the first one, the columns in the second, is equal to E root 2A. Well, let's solve for B. What do you say? That's the easier one. Move this across. I have EB is equal to a times 1 or square root 2 minus 1. Divide out the b or e's, not the b's, and you get b equals a times root 2 minus 1. Not done yet. Let's just set a equal to 1 to make life easy. I put a c out here for a normalization constant. Or I could have just put a out here since that is. And so the last step in finding what 1 is I normalize it. And remember, we're just going to use the real here, so I'm going to save myself some time, not put any stars or anything. So now multiplying through, that's going to be 1 equals a squared times 1 plus root 2 minus 1 quantity squared. Well, phooey. Root 2 minus 1 squared is going to be 2 minus 2 root 2 plus 1 equals. Usually problems don't have ugly answers like this in textbooks. They just choose them to be pretty, which makes me wonder if I made a mistake somewhere. But that's what I got. I got to go back and just double check up above. It surely seemed right when I had plus or minus square root 2, but did I make a mistake there? E squared. Okay, minus e squared. And then minus e lambda plus e lambda plus lambda squared minus. Yeah, I think that's right. Just had to double check. So now I have found my 1. And so I have 1 over square root of 4 minus 2 root 2. That's what it was, right? That's my state 1. And then how do I find state 2? Yeah, basically the same process, except for I'm going to put in the other solution. So for state 2, I'm going to have, do you mind if I rewrite over the same thing? A minus there. That's the only difference. So I have a minus here, which means that both of those are negatives. And so when I do this one, I'm going to have that state 2 is equal to a1 minus root 2 minus 1. And then I have to go through my normalization process again. Now notice minus root 2 minus 1 does not have the same magnitude as root 2 minus 1. So I don't expect to get the same I don't know why I put a divisor there. There's no divisor. So now I'm able to finish out. You recognize this is equal to 1. And so A is equal to 1 over square root of 4 plus 2 root 2. So there's state 2. Now a sanity check. These, we've already forced them to be normalized. Are they orthogonal?
We have to take the product.
Yes. We started with the understanding that they're orthogonal, but now we're going to check. So to check the orthogonality, I'm going to have looks really ugly. Fortunately, since I'm only checking for orthogonality, I don't really care what the outer portion is, the 1 over square root 4 minus 2 root 2 times 1 over square root 4 plus 2 root 2. Although it turns out to be easier than you'd think because you have the cross terms come out to 0. But what I care about the most is 1 plus root 2 minus 1 times minus root 2 minus 1. See, no, that's a minus. It's like, that doesn't come out to 0. You have root 2 times minus root 2 gives you minus 2. And so 1 minus 2 is minus 1. Minus root 2 plus root 2, still minus 1, plus 1 is 0. And this just was multiplied by the square root stuff. So it's orthogonal. One more thing. So we'd done all of this last class period, except for the first step where we took from the Bra-Ket indicator of the Hamiltonian to making it a matrix. Right. So that's what I like about this problem is it makes you go through that step. But then there's one more thing. This is, shall we say, a pair of perpendicular directions, right? Because they're orthogonal. But we could change the orientation as long as we keep them perpendicular and we'd be fine. Actually, since this is two-dimensional, I guess I should go like this by changing the orientation. And so we do that through a similarity matrix. And at this point, you should be saying, what in the world is this similarity matrix? Why are you springing all this stuff out on me? The last lecture before the exam. The similarity matrix is a transforming matrix as indicated here. Like, what? Okay, so the inverse similarity matrix is formed by taking our three normalized solutions in this case, or two in the one we did, and slamming them together. So making the similarity matrix is super easy, doesn't require any thought. But we have to do the conjugate of it, or the inverse of it. But because this is a unitary matrix, the inverse of it is just the transform. So what we've done here is the trace stays the same and everything else flips positions. So the transform is just taking the thing that was 1, 1 becomes 1, 1, 1, 2 becomes 2, 1, 1, 3 becomes 3, 1, and so on. And how that's useful then is we transform our operator by putting S, A, inverse S. Now, we're going to come back and we're going to finish this problem doing the transformation, and then we'll come back. So in this case, since these are our two eigenvectors, then S minus 1 is equal to, and this is going to be ugly. So I'm going to put the first one here. So the first term and the first one, I have to bring the normalization term inside now. 1 over square root 4 minus 2 root 2. And then this one here, root 2 minus 1 times, or divided by square root of 4 minus 2 root 2. So that's, I put ket 1 there. And now I'm going to put ket 2 beside it. 1 over square root of 4 plus 2 root 2. And minus root 2 minus 1 over square root of 4 plus 2 root 2. That's my inverse transform. How do I make my inverse similarity matrix? How do I make my regular similarity matrix? It's almost legible. So if that's S minus 1, how do I make S? I flip it, right. So the first is going to stay the same. But then this term here, the black one you can see, is going to be put over here now. The bottom corner is going to be the bottom corner that we had before. And then the one that remains, that one, 1 over. Now this is so ugly, I don't want to continue the math. But what we can do now is we can take this and we put, and I'm really going to have to add another page to this, just one. We can now put our Hamiltonian prime is equal to S Hamiltonian S minus 1 equals, oh, I don't want to write that. To make life easy on us, I'm going to put A, B, C, D, A, C, B, D. Right, that's just going to be a lot less writing. And then in the end, we'll look what all of these A, B, and so on are. So now we have to do the matrix multiplication. The reason I'm continuing on is because you have to see how this goes. If I'm going to multiply these matrices, I'm first going to multiply these two matrices. So what's the process for multiplying the matrix? I ask this, and how I want you to answer is to tell me, what is my term right here? Go ahead.
Plus B.
Okay, so there's my first term. What about the one below it? The one below it is going to be using the lower one here with the first column. So you're doing one row with one column. So the upper row is going to be the upper rows here. So the upper row with the first column is first row, first column. Upper row with the second column is first row, second column. Lower row is going to be second row, first column, or second row, second column. So here is going to be CE plus DE. That's this with this, and then this with this. Now, second column, first row, that's going to be A with E. First row, second column, and then B with minus E, so minus BE. And finally, what's the last one going to be? Right. And we've got one more multiplication. This one here with this one here, right? A squared E plus ABE. And then this one with this one plus ABE minus B squared E. That's my first term. That was from minus BE times B. You see? Okay, so what about the one below it? What am I going to get? Okay, wait a minute. I wrote the wrong thing. I think I was blindly following along. We go over to this one with this one. So you might have said that right. I certainly wrote it wrong. Minus BC or plus BCE minus BDE. And then we've got two more to go. So ACE plus bis plus ace minus bis. Uh-oh. Ran out of space. And finally, c squared e plus cde plus c squared e minus d squared e. Now, if I made no mistakes, which is at this point a 50-50 at best, then it should turn out that when I multiply these through, and it's just going to take forever to do it, and we don't have that kind of time. We only have 9 minutes left, and we haven't reviewed. This here should give me 0, and this here should give me 0. And then this should be square root 2e, and this should be minus square root 2e. It should give me, whoops, I put the box around the wrong thing. It should give me a diagonalized matrix where my lambdas are the trace elements. And we can also go through and we can transform. It will also give me a new 1 prime equals 1, 0, and 2 prime equals 0, 1, which makes life much easier. So I didn't do the last steps here because we just don't have the time. It takes too long. The reason it takes too long is because, well, we had a crazy normalization constant. So the example I was going to do for you, this one here, comes out with eigenvalues that I worked out at the very end of last class period that lambda 1 was 3, lambda 2 was 2, and lambda 3 was minus 2. And then when you go through and you find, well, yeah, this did not have redundancy, so it was easy. You find your eigenvectors and you get these eigenvectors. Then from reading directly from those eigenvectors, you get your inverse similarity matrix and your your similarity matrix. And then when you do this math, it's a lot easier because you have not as many terms to write around. And there's a bunch of zeros. And so it ends up giving you the trace elements are the eigenvalues. And so that's the beauty of this. We now have it rotated, changing what our directions for X, Y, and Z are, so to speak. They still have to maintain their perpendicular nature, but now we have the state gives me the eigenvalues. So these are the states. This is a diagonalized operator, and then its eigenstates are the ones that you want. And here's how you finally do the transformation of each of your eigenstates if you wanted to, right? You can take this and you can immediately say, aha, the eigenvalues are 3, 2, and 1. And so I have 3, 0, 0, 0, 2, 0, 0, 0, minus 2 times A, B, C equals 3 times A, B, C. And what's your first equation? 3A equals 3A. Well, that was tough. And then I have 2B equals 3B. How can that be true? That's only true if B is equal to 0. And likewise, I have minus 2C equals 3C. That can only be true if C is equal to 0. So you see right away that you have 1, 0, 0 is your normalized eigenvector.
Wait, but you had to go through and actually find the eigenstate before you could
Yes, before you can do the transform, yeah.
So I don't understand. Would we just have to do one or the other? Like, because I went through all of that base work to get to A prime where your eigenvalues
Yes.
are the trace elements.
Yeah.
and then you could do the transform and find your eigenstates.
Yeah.
But are we going to be doing the transform to find the eigenstates, or are we going to be finding the eigenstates through using that all the math that came before?
Okay, so that's a good question. It depends on what they give you. If they want you to find what find the normalized operator and find its eigenstates in terms of the original eigenstates, then you have to go through this.
What do you mean?
Well, if it's in terms of the original eigenstates, then your original eigenstates would have looked like 1 0 0 0 1 0 0 0 1, and then these are going to be combinations of each of those to give you the new one. Given that we only have 4 minutes, I'm going to stop my explanation there and take a quick breather on reviewing for the test, because we have very little time. So this is a review of what we've learned so far in this class. So starting at the very beginning, the origins of quantum mechanics. Don't forget where we've come from here, because it's only starting maybe to make a little sense. But if you keep in mind the history of how it progressed, it makes it so you can put it into a little more context of this is why they did it, and these are all the things that have come from it. So developed to treat the wave nature of objects, things that we think of as particles having a wave nature. And you have the waves or the matrix methods. Operators are mathematical functions that extract information, and the eigenstates are the functions that contain that information that needs to be extracted. And our steady states represent, a state that has this eigenvalue. It's all based on statistics. So we have things like being able to calculate the average value if you take a large number of measurements that we call the expectation value. So you should be able to relate probability, expectation value, and standard deviation, right? And you've done a lot of problems with those. The wave method was designed or devised by Erwin Schrödinger. And when we're going to use that, we separate the time portion from the spatial portion, and we just solve the spatial portion. Because the time portion always has the same thing. Remember on the last test, you had, now that you have the spatial portion, what's the full wave function in terms of space and time? And your wave functions, of course, have to be normalized and mutual orthogonal. Matrix method is what we've just been learning about briefly. Heisenberg was the one that started this process. He didn't know any of this linear algebra stuff. You don't know it either. You're in the same boat. And so he had to learn it just like you are. The wave functions are now represented as vectors, and the operators are matrices, and you still have all of the information in that matrix, and you have to extract it by doing that characteristic equation that we've just done today, and then finding from those eigenvalues what the eigenvectors are. Don't forget the whole Brock, our textbook. He's so funny. I don't know where the C went. Did you guys read that? Yeah. Well, I thought it was kind of funny. Inner product, same idea as a dot product, and it's the integral it's equivalent to that. So all of these things really mean the same thing. Uncertainty relations, we've gone through uncertainty relations a couple of different ways. So now you have a better understanding of where it comes from. I don't expect you, by the way, to be able to replicate all of that stuff where we came to the generalized uncertainty relation. But if you're given that generalized uncertainty relation, you should be able to calculate the commutator and whatnot to find a specific uncertainty relation between two variables.
So you don't need us to go through the time dependence of?
No.
Okay.
No. Just be able to use the outcomes.
Okay.
Otherwise, you're out of luck. I think I would have been at least. Okay, the exam itself, it'll focus more on understanding things, and the small problems really will be smaller this time. So it's primarily to make sure that you're ready for the hydrogen. You have the foundational stuff. What we finish now is the foundations for quantum mechanics, and we're ready to do our first actual problem. Our first and only actual problem, hydrogen atom. So that's what we have coming.
How much matrix math is going to be on there?
I imagine, okay, so I would have to think, but I'm pretty sure you'll have something like say this and say, find the eigenvalues and the eigenvectors.
That last part that we just briefly.
Not the transformation part, no. Because I just sprung that on you now, right? It's only one lecture.
Would you ask us theoretically what a similarity matrix is and what it does?
No. Like I said, I just sprung it on you now. I don't want to give it to you the last 5 minutes of the last lecture before the test and say, now make sure you know it. So everything I did before that, we had done the previous lecture. I would consider that fair game.
Okay.
Just not the stuff that was brand new at this one.
And you said problem 23 was a good one to know.
Well, that's the one we just did.
Right,
but
is that like
the reason I liked it was because you had to go from this to making the matrix. It didn't give you the
something like
matrix.
That could be a small problem.
There could be something like that, yes.
Okay.
All right. Question, Trent?
Is the one that you didn't finish the example